Okay, so here we are with lesson 3, and we're looking at all possible combinations,
Sure.
which is a little bit different. In the previous lesson, we looked at the number of ways of choosing R items from a set of N distinct items. So we basically looked at NCR.
Yeah, I've got 10 things, but I want to know how many ways I can choose 3 of them. So we
Okay.
knew what that R was, 3 or 2 or whatever it was.
So today we're going to look, though, about questions where we want to count the number of combinations of any size. So all R values, anywhere from 0 to N. So I want to look at, okay, well, how many ways could I choose 4 items? And how many ways could I choose 3 items?
Yeah.
And how many ways could I choose 2 items, 1 item, or 0 items?
Oh my gosh.
How many ways could I choose all of the combinations if I don't have to just choose R, if I can choose anything I want, any number that I want? In this way, basically, we're going to be finding the total number of some subsets of a given set of items.
Yeah.
All the subsets of a given set of items.
Picture that you've got 10 snacks on your counter, and you want to know how many ways could you grab some snacks.
Mm-hmm.
And you want to know, I could grab 1 snack or 2 snacks or 3 snacks or 4 snacks or 5 snacks, all the way up to 10 snacks.
Yep.
And each of those ones has its own whole different host of possible combinations. And so when we say all possible combinations, we're actually saying, like, how many ways could you choose some of N?
Mm-hmm.
Right? And so this is, yeah, here we go.
All right.
It gets good.
So let's start out with a money example. How many different sums of money could you make with a penny, a nickel, a dime, and a quarter? Okay. So this is all possible combinations of 4 distinct items, because one sum of money could be just a penny,
or just a nickel,
or just a nickel, or just a dime, or just a quarter, and that would be like choosing one item.
Yeah.
But I could also make a sum of money from a penny and a nickel, or a penny and a dime, or a nickel and a dime, or a dime and a quarter, and so on and so forth. So I could choose one item, or I could choose 2 of the items, or I could choose 3 of the items. They all make a sum of money.
Yeah.
So let's basically lay this out in a very organized case-by-case analysis of the different sums.
So we're going to do a logical list, again, just like we did in the beginning of this module when we didn't know how to calculate it, and then we'll show you how that correlates to the calculations.
Yeah. So basically, here is case number 1. I'm taking either a penny, a nickel, a dime, or a quarter.
Just one thing.
One thing. Here's case number 2. I'm going to take a penny and a nickel, a penny and a dime, a penny and a quarter, a nickel and a dime, a nickel and a quarter, and a dime and a quarter. That's 2 items.
Yep.
Here's 3 items. A penny, a nickel, a dime, a penny, a nickel, a quarter, a nickel, a dime, and a quarter, or a penny and a dime and a quarter.
Yeah.
And the last case is, of course, taking all 3.
All 4.
Excuse me, all 4.
You got it.
All right. So if I was to add up these different cases, well, how many different combinations are there? And remember, these are combinations, because penny and a nickel is the same sum of money as a nickel and a penny.
Yeah, we don't care
so
about the
we don't care about the order again. So these are combinations. So in the first case, I've got 4 choose 1, which is 4 different possibilities. In the second case, I've got 4 choose 2, which is 6. In the third case, I've got 4 choose 3. And in the last case, I've got 4 choose 4.
What's the only one? I've got 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4.
The only one that I don't want is 4 choose 0.
Because that would be no money.
Because that would be no money, and that's not a sum of money.
That's right.
Basically, what I have is I've got 15 possibilities here.
Yeah.
Okay? So this is a lot of work, because this is 4 items.
Yeah.
And if we were to run through this with 4 different cases, what if we had 5 items? What if we had 6 items? This would be a lot of work to add up.
It would be a lot of cases.
Okay?
Yep.
But this is how we do it, and this is how we logically think about it.
Yep.
Alternatively, another way to think about it is that for each coin...
Imagine each coin is a stage.
Yeah.
And you're standing in front of stage 1, which is coin 1, which is the penny.
And we can either include it, or we cannot include it. We have 2 choices for that stage.
And then we move to the next coin, and we can either include it or not include it. And then we move to the next coin, include it or not include it. So what you end up with is each coin represent a stage. So now we're sort of, mentally, we're going to go back to permutations where we're making choices at stages. The number of choices at each stage here is 2, right? And I want to make a choice at each stage. I want to decide whether or not to take the penny, whether or not to take the nickel, and so on.
And so what I get is 2 times 2 times 2 times 2, which is 16. It's important because there's one case out of this whole thing where I haven't included a penny, I haven't included a nickel, I haven't included a dime, and I haven't included a quarter, that's one case that's called the null set.
It's one way of choosing nothing.
And in this case, a sum of money isn't zero.
Yeah.
0, 0.
Yeah.
So we want to subtract off that null set. And so 2 times 2 times 2 times 2 is 2 to the power 4, which is 16. Minus 1 is our 15, which is the same answer that we got
From
one
above.
slide before.
Now, if you look at what you've written on the slide before in your own notes, recall that the only case we left out was 4 choose 0.
Yes.
And when you type 4 choose 0 into your calculator, you're going to get 1.
Yes.
Because there is one way, there is one option you have of walking away with nothing.
Yeah.
The question is whether you want to have that option of choosing nothing,
or whether
you want to
don't.
remove the option of choosing nothing. So
Sometimes it's okay to have the null set.
Sometimes it's okay to walk away with nothing.
Yeah.
Yes.
And
In
we're
this
gonna
case,
we're gonna see a
not so
couple
much.
of examples of that.
Yeah.
So some formula for you: a subset with n distinct elements has 2 to the power of n subsets, including the null set.
Yeah. So that includes the option of choosing nothing.
Mm-hmm.
If you want to remove the option of choosing nothing, if you want to remove 4 choose 0, then you have to take 2 to the n, and then you just minus that 1.
And you minus.
Or you minus 4 choose 0 if you feel better. But that's exactly what we're doing there.
Okay, so a cartoonist has 5 pens, each with a different color of ink. How many different color combinations could the cartoonist create in one panel of his graphic novel? Well, if we have 5 pens, these are going to give us our color combinations.
And order doesn't matter. It's not a color permutation.
No.
No.
No, no. Is no pens a color?
If we leave it without any color, is that a color? No.
And so the answer is no. So we're going to subtract 1.
Yeah, the null
So you'll notice
set is out.
this is, whenever we encounter these questions, this is one of the first things that we ask ourselves. Okay, so is the null set? Should we include it? Should we not include it?
Yeah.
In this case, no color. If we're asking for color combinations, no color, so not using any pens, is not a color combination.
Yeah, so it's
right?
not an option.
So it's not an option.
Yeah.
So here we go. We've got pen number 1, include it, not include it. Pen number 2, include it, not include it, and so on and so forth. And we subtract off the null set. 2 to the 5 minus 1 is 31 different color combinations that this cartoonist could use.
Yeah. So our n was 5. Our 2 to the n is 2 to the 5. Since walking away with nothing is not an option, we subtracted the null set.
Yep, exactly.
And there we go.
All right. So what about, instead of having a number of distinct items, we have a number of repeated items.
Okay.
And they're indistinguishable. So there's some identical items included here.
Yeah. Or they're essentially indistinguishable, or we don't care to distinguish them. Like in this example, you can tell one tulip from another tulip, but if I don't care to tell one tulip from another tulip, then we just treat all the tulips as being just the same thing.
Yeah.
Yeah.
So our florist here has 6 tulips, 4 daffodils, 8 crocuses, 2 irises, and from these we're going to make a flower bouquet, right? So how many different combinations are available for the bouquet? We're taking anywhere from 1 flower, 1 single tulip to give,
All the
or
way up to all of them.
all of it
Yeah.
in a huge bouquet with every single one of these flowers as the bouquet. 4 different kinds of flowers.
Yep.
Right? So we can choose anywhere from 0 to all of them in the bouquet.
Yep.
Really, though, now you have to think about this.
All right. Is it still a bouquet?
Can I give you a bouquet
of no
with
flowers?
no flowers? I've given you many of those bouquets before. How many is it a bouquet if there's no flowers in it?
Yeah.
And I would have to say the answer is no.
No.
You're not giving your friend a bouquet of flowers
It's
if
the
there's no
thought
flowers.
that counts, Mr.
Yeah,
Jackson.
I know. So if there's no bouquet, if there's no flowers, it's not a bouquet.
No.
So the null set we don't want to include.
Yeah.
This is
So
another
n
example.
choose 0. We're going to take it out. We're going to subtract out that null set.
All right, so here we go. So basically we got tulips, we got daffodils, we got crocuses, we got irises. For the tulips,
there are 6 of them there.
okay, so we could choose to include 1 or 2 or 3 or 4 or 5 or 6 or
none.
None. So there's 7 options to include for tulips.
Yep.
Daffodils, there's 4 of them. In the same way, we can include 1 or 2 or 3 or 4 or none.
I could say I don't want daffodils in this bouquet.
So there's 5 options. Crocuses, there's 8 of them, so we could include anywhere from 1 to 8
Or the
or
ninth
none.
option, which is none.
So and so on and so forth. But again, here we are with our one case
Where we
we're
might
gonna,
have chosen none, 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 and none. Oops. Wait, we don't
we
want that.
haven't given
We
a
can't
bouquet.
have that.
So we're going to subtract off the null set, and what we get is 945 minus 1, which is 944 different bouquets that you could give.
Yeah.
Or that could be created, I suppose.
So notice here, all we did was we lined them up in groups.
Yeah.
And that group, however many there are in that group, we can take any of those, or we could take none. So we've added an option every time. 6 tulips, 7 options. 4 daffodils, 5 options. 8 crocuses, 9 options. 2 irises, 3 options. This is just like if you were writing a true-false test, and you had 5 questions on the true-false test, and you had the choice of answering true or false or leaving it blank. So this is like that, leaving it, we add that leaving it blank option in. We have it leaving the tulips on the ground and walking away with none.
Okay.
So
to count all the possible combinations, let's use this formula. Here it is. The total number of selections or subsets of at least one item that can be made from a set of P items of one kind, Q items of another kind, R items of a third kind, and so on and so forth, is P plus 1 times Q plus 1 times R plus 1, all the way up to N plus 1.
Yep.
And then we subtract off the null set if we don't want to include the null set.
Yep.
Of course, we wouldn't subtract it off if we didn't.
Nothing is a viable option.
Yes.
Yes.
All right. So let's go back to some money.
Yeah. We had like 1 penny, 1 nickel, 1 dime, and 1 quarter in our original example. Now let's say we got a pocket full of change here.
4 pennies, 2 nickels, 6 quarters.
There we go.
How many different sums?
Okay.
Well, for the 4 pennies,
it's a penny pile.
Yeah, I could include all 4 or none.
Yep, so there's 5 choices.
For the nickels, 2, 1, or 0.
3.
For the 6 quarters, I could include all 6, or I could include none.
7 choices.
Right, 7 choices. Again, we come to a sum of money. Is no coins a sum of money?
If you're going to hand somebody some money,
you can't give them nothing.
So we'll take out the null set.
So we take out the null set. We have 104 different sums of money that we could give.
Yep.
All right. So Rachel walks into a bookstore looking for 6 books on her list.
Yeah, so she's got a list. She's got 6 books on there. She's walking in. She's hoping to find something. How many possible combinations could she find? Well, she could find all 6. She could find 5 of the 6. She could find 4 of the 6, and so on and so on. We have to ask ourselves, is it possible for her to find none of them?
And I would have to say yes.
Yeah, it's possible. They're not
She
carrying
could walk in there and she could find none of the books that she was looking for.
Yeah.
The null set in this case is a viable option.
Nothing is a viable option.
So we want to include that. So basically, she could find anywhere from no books to all 6 books. So let's include the null set.
We won't subtract out the 1.
Exactly.
That's essentially what we're doing here.
And so basically, our first book, find it, not find it. Our second book, find it, not find it. Our third book, find it, not find it. And so on and so forth. We get 2 to the power of 6. We have 64 different combinations of these books that she could find.
Yep.
Now, she walks out of the store having made a purchase.
Based on her list.
Yes. So same list as before, but now we give you some more information. She's made a purchase.
She bought something.
How many possible purchases could she have made? Okay. Can you purchase no books?
You cannot.
You cannot purchase no books.
So nothing is not an option. The null set is not an option here.
Yeah.
We will want to subtract out.
So now we have, you can't purchase 0 books.
No.
So now, the distinguishing fact between the two is that you can walk in and find no books on your list, but you can't walk in and make a purchase of no books on your list, right?
Yeah.
So basically here we have 2 to the power of 6, and we subtract the null set, and so we'd say 63 possible purchases.
Yeah.
Okay, so it's answering a different question, or a different kind of question.
Yeah, just have to think about, is nothing a viable option?
Mm-hmm.
And if it is, keep the null set. If it's not, subtract the 1.
Mm-hmm.